Hey guys, and welcome to our last lesson of the week. So this lesson is going to be called mole ratio. So if you've ever worked with ratios in math before, you know it's a relationship between one thing and another thing, and it's kind of like a conversion. So a mole ratio is just going to be a conversion between the number of moles. So we're going to be converting from moles to moles. Before we get to this, we want to talk about the idea of a balanced chemical equation. The reason we spent so much time on balancing in Unit 1 and Unit 2 was because balancing is so important in a mole ratio. So a balanced chemical equation is really just going to tell us the ratio between the number of products and the number of reactants. So for example, let's take a look at water here. In this case, I'm always going to have two water molecules being formed for every two hydrogen, and this lack of number here means a one, so one oxygen. So that in itself is a ratio. So at the molecular level, the ratio of the components is two hydrogens, one oxygen, and two molecules of H2O. So we can use this ratio to answer some meaningful questions. So first question we could ask, what would you do if you wanted to produce twice as many molecules of water? Well, let's think about this. If I wanted to produce twice as many water molecules, if I wanted to produce 4 instead of 2 water molecules, that would mean everything else would double. So rather than having 1 oxygen, I would have 2. And rather than having 2 hydrogens, I would have 4. So the idea of this ratio, and we actually call this a fixed ratio, is if I want to double one component, I doubled water in this case, I have to double all the other components as well too. So that balanced chemical reaction, those numbers in your balanced chemical reactions actually are what's setting your ratio. A little bit more of a challenging question, and how we might actually have to set up a molar ratio, is what if you wanted to know how much oxygen is needed to produce 20 molecules of water? So let's say that you needed 20 molecules of water. The question is, how much oxygen would you have to produce? You could go through and try to play with the numbers a little bit. That's a little bit more challenging. So this is where your concept of the molar ratio comes in. So this is going to be your molar ratio, your general setup. Sometimes this can seem a little confusing, so just bear with me for the first example. I'll do 2 other examples after that. It might make a little bit more sense. So what we do is, to set up your mole ratio, you always start with the number of molecules you have. Sometimes I actually like to change this to given. So this is going to be the number of molecules that you're given in the question. The number of molecules that you need, I sometimes like to change this to the word want, or even simpler, we're actually just going to call this X. So the number of molecules that is needed is actually the number of molecules that we're asking about. So in the question, if you go back and you read this question, they're actually asking about how much oxygen is needed. So what we're looking for, what we want, or our X value that we don't know, is number of oxygen molecules. So oxygen would actually go on the bottom here. Here, we have the number of molecules from the equation and the number of molecules from the equation. So all that means is from your balanced chemical equation. So this side here is always going to be your coefficients, those big numbers, from your balanced chemical equation. So we're going to use that oxygen example. I'm going to walk you through this, and then we'll do 2 examples in a little bit more detail. So we are going to have to set up the ratio. So I'm going to leave that at the top for now, and we're going to reread our question. And our question is telling us that we want to form 20 molecules of H2O. So the information that we were given is 20. So that 20 is going to go just right at the top here. So this here is going to be H2O. We're looking for information about oxygen. So oxygen is how much oxygen is needed. That's our X value. That's where we're trying to end up with. So oxygen is going to go at the bottom. I actually don't know how much oxygen is needed, so I'm going to call that X. So that's where that algebra kind of comes in, and we're going to call this value X. we're also going to go back and we're going to look at our balanced chemical equation, because remember, on this side, we're looking at our balanced equation. So if I go back and I look at my numbers for my balanced equation, I want to keep water. See how water's in the top here? I want to keep water in the top. So if I take a look and see what number is in front of my water molecule, I'm going to find that there's a big 2 in front of water. So I've got that 2 is coming from that coefficient that's in front of water. And then in the bottom, I have oxygen. So I want to keep that 1 in the bottom. So notice that both oxygens are on the bottom and both both waters are on the top. So those are always consistent. You want to make sure your ratio is the same. You want to make sure that you have the same molecule in the top as you do in the bottom. All right, so our next step, we are going to have to go through and solve for this. In order to solve for this, we are going to do something that you might remember from math, and that's going to be cross multiply. So cross multiplying looks like this. I'm going to go ahead and I'm going to multiply these two things, and I'm going to go ahead and I'm going to multiply these two things. So let's start. I'm going to use different colored arrows so we can see this. Let's start with my first round of cross multiplication. I'm going to start going across here. So I'm going to use this purple here, going across here. And in this case, I'm going to end up with X molecules of O2, and that's going to be multiplied by 2 molecules of H2O. I'm then going to cross multiply my other side. So I'm going to use, I'm feeling green today. Let's use this green here. I'm going to cross multiply this section, and that means I'm going to have 20 molecules of H2O times 1 molecule of O2. Now all that we have is like an old school algebra where I'm trying to solve for X. So in this case, I'm looking for X molecules of O2. I want to go ahead and I want to get X by itself. So in order to get X by itself, I want to go ahead and I want to divide both sides by 2 molecules of H2O. So if I divide this side by 2 H2O, it's going to cross this out. And what this is also going to do on this side is this is going to cross out these H2Os as well too. So not only have I gotten X by itself on the left-hand side, but now I've gone ahead and I've crossed out my H2Os. So now I'm just left with dealing with molecules of O2. So that shows this here. So now all I have left to do is I'm going to take this 20, I'm going to multiply it by this 1, and I'm going to find that my overall answer is going to be that I'm going to have, oh, I forgot to divide by 2. Look at me, silly. Got to divide by this 2, and I'm going to find that overall, I'm going to be left with 10 molecules of O2, and if you take a look, my unit is actually also correct. My waters, my H2Os have canceled each other out, and I'm going to be left just with O2. So that's how we would go through and we would set up a molar ratio. Something you might have been able to figure out before, but as we get further along in chemistry, you're going to find we're going to start introducing decimals rather than whole numbers, and it's going to be a little bit more challenging, and you'll need that molar ratio in order to figure it out. So we're going to take a look at our first example, and this is really realistic of what you might see in chemistry. So we're going to look at the combustion of octane. Really, all that matters is our balanced chemical equation here. So we're going to be using our balanced chemical equation and our coefficients that are in front. And we've also been told that we have 450 molecules of water, and it's asking about the amount of carbon dioxide. So you always have to think about where we're starting and where we're going. So this question is asking us, it's giving us information about water. So water is here. And it's asking us information about carbon dioxide. Notice that it actually doesn't say anything about oxygen, and it doesn't say anything about octane. So that means we can actually essentially ignore oxygen. We could ignore octane because all I care is about the relationship between carbon dioxide and water, because that's what the question's asking. So let's go through and let's see how we would set up this molar ratio. So I'm just going to slide this over here. And remember, I was given the information of 450. So I'm going to start with what I was given. So I was given the information of 450, and that was 450 molecules of H2O. And what I'm looking for, my X in this case, is going to be how many carbon dioxide molecules is required. On this side, remember I'm always using my coefficients for my balanced chemical equation, and I want to keep my molecules the same. So I want to make sure that H2O goes on top, and I want to make sure that CO2 goes on the bottom. If I slide back here for a second and take a look at my balanced chemical equation, I'm going to find that the number next to H2O is 18. So I'm going to put my 18 on the top here. And I'm going to find that my number in front of CO2 is 16. So I'm going to put a 16 on the bottom here. Now I can go through and I can cross multiply. So let's get our, well, we don't need colors. We can make this work. So we're going to go through and we are going to cross multiply. So by cross multiplying, let's start with my CO2. So X CO2, and I'm going to multiply that by 18 H2Os. That's going to be equal to 450 H2Os, and that's going to be multiplied. That little dot means multiplied, 16 CO2s. Now I want to get X by itself. In order to get X by itself, I want to take this H2O and I want to move it to the other side. So I'm going to take my XCO2 and I'm going to take my 18 H2Os and I'm going to divide this side by it. What that's going to do is it's going to go ahead and it's going to cancel out my H2Os. So I'm going to cross out H2O, I'm going to cross out H2O, and look at, I'm left with CO2, which is the unit that I want to end up with. Now all that I'm left with is a little bit of fancy math. So all I have left to do is I'm going to take 450, I'm going to multiply it by 16, and I'm going to divide it by 18, and you're going to find it is going to give me, we have the long version here, you're going to find if I go through and I do all that math, it's going to leave me with 400 molecules of CO2. So notice this is just a longer way that we set it up. We have our 450, we have our 16, we're dividing by 18. If I plug that whole thing into my calculator, I'm going to be left with 400 molecules, and my unit in this case, CO2. So 400 molecules of CO2. All right, let's take a look at our other example. Before we get to our other example, I want to introduce or reintroduce this idea of the molar ratio. So notice that we are using the word molecule, but this whole title of this note is called molar ratio. So a molar ratio is exactly that. Rather than using molecules, it's going to be a relationship showing the number of moles. So we're going to look at a theoretical example, and then I'm going to go through a real example with you. So let's go back to our water example. Before, we were talking about the molecules of water. So we had 2 molecules of H2, we had 1 molecule of O2, and we had 2 molecules of H2O. Now in a molar ratio, I want to talk about number of moles. So how am I going to convert this to number of moles? I would multiply everything by Avogadro's number. So I would multiply 2 by Avogadro's number, I would multiply 1 by Avogadro's number, and I would multiply 2 by Avogadro's number. Well, since we've done the same thing, the ratio is actually going to stay the same, right? Since we're doing the same thing to each of them, I can kind of ignore that number, and my ratio is going to be the same thing. So I'm still going to have 2, just like I did in the start. I'm still going to have 1, just like I did in the start. And I'm still going to have 2, just like I did in the start. But take a look at what changed. My unit changed. So now for a molar ratio, I'm not talking about comparing the number of molecules anymore, because I was talking about molecules up here. I'm talking about the number of moles. So for every 2 moles of hydrogen, I have 1 mole of oxygen, and I have 2 moles of H2O. So we're going to do the exact same thing, but now this time we're going to use the term mole instead of the term molecule. So for the mole ratio, it's going to be the number of moles that I have, or the information that I was given. Let's go back to green. Look at, I got a Christmas vibe going on. So this is information I was given. This is going to be my X that I'm looking for, and this is going to come from my balanced chemical equation. So let's do another example for the mole ratio. This example, look at, I was given what could be intimidating chemical equation. We gave you that just to show you. It doesn't matter how intimidating the equation is. All that matters is using those numbers, those coefficients in front of it. So in this definition, we have the decomposition of malachite, and we were also given the number of moles that we're dealing with, and the number of moles is 0.0045. So let's go through, let's do this as an example. So I am going to start with the number of moles I was given, and the number of moles that I was given was 0.0045, and that was 0.0045, that was moles, and that was for this compound Cu2, CO3, OH. I'm looking for information about, well, let's go back and let's read my question. What amount of moles of copper oxide, Cu, forms with malachite? So I'm looking for X moles of copper oxide. That means I only have to look at Cu2, CO3, OH2, and Cu. I don't have to look at anything else in my balanced chemical equation. So I want to make sure that I keep my molecules the same and consistent. So on the top here, I'm going to keep this compound. And on the bottom, I'm going to keep this compound. Let's switch back to my balanced chemical equation and see what coefficients need to go in there. So I'm going to take a look at my balanced chemical equation, and I see no number written in front. So that no number would be a 1. So I'm going to go ahead and I'm going to put a 1 on top of here. And then if I go back, I see a 2 written in front of copper oxide. So I'm going to put a 2 in front of here. Our next step is to cross multiply. So I'm going to multiply this way, and I'm going to multiply this way. To cross multiply, that means I'm going to have X moles of copper oxide, and that's going to be multiplied by 1 mole of Cu2, CO3, OH2. I'm then going to have my 0.0045 moles of Cu2, CO3, OH2, and that's going to be multiplied by 2 moles of copper oxide. I then want to go ahead and I want to get this X by itself. To get an X by itself, I need to take this value here and I need to move it to the other side. In order to move it to the other side, I need to divide. So I leave my numerator the same. I don't touch that. And in my denominator here, I'm going to have my 1 Cu2. Geez, you think I could have picked a smaller compound, eh? That's okay. By doing that, I can go through and I'm actually going to cross out this unit here. I'm going to cross out this unit here, and I'm going to be left with the unit of CO, copper oxide, which is actually the unit I'm looking to report. So if I take 0.0045 and I multiply it by 2 and I divide by 1, I'm going to find the number of moles of copper oxide that are going to be produced by this decomposition reaction. 0.0090 moles of copper oxide. So you can see that that's something that you probably wouldn't be able to do in your head. So that's why it's important to be able to set up these molar ratios. You have a couple practice questions in the homework there for you. So if you can go ahead and try those, this molar ratio is going to be really important when we get to stoichiometry next week. All right, good luck on your assignment this week, and we'll see you guys next week. Bye.